we finally have all the tools we may need to build the general form of the expectation maximization algorithm. So let's start with the formulation of the problem. Say we have a latent variable model. So we have latent variables t which are not observed, which are latent, and variables x which we observe. And we have marginal likelihood, p of x given parameters, which can be expressed in terms of the model, the likelihood and the prior, as summing the full joint distribution p of x and t given theta with respect to all the values of t, so marginalizing out t. And we can write down this full joint likelihood as a product of the p of x given t and the prior p of t. So this is how the marginal likelihood looks like, and we would like to maximize it. So our problem here is to maximize the likelihood of our dataset, the density of the dataset given parameters with respect to parameters. And this is marginal likelihood because we don't observe latent variables, so we have to marginalize them out. Well, first step, as it usually happens in these kind of problems, let's take the logarithm of our likelihood, because it will turn products into summations and make everything easier because of that. Next step is to assume that our dataset consists of n objects, which are independent given the parameters, which is kind of standard in all machine learning problems. And finally, we can turn product into summation by using the property of the logarithm. And we have a function like this, which we want to maximize with respect to parameters, right? One more step, we can substitute the marginal likelihood of the data object xi by its definition, which is sum of the joint distribution with respect to the values of ti. And finally, we have a function like this, which we want to maximize. And as we have already discussed in the previous module, on the Gaussian mixture model case, it can be in principle maximized with stochastic gradient descent, but sometimes it's not the optimal choice to do. So we want to do something else, something better. Well, the general idea would be as follows. Let's build a lower bound for this thing by using the Jensen's inequality. I don't give you details here. They will come in the next few slides. But let's assume that we can lower bound this thing by some function which is easy to optimize. In this case, instead of maximizing this original marginal log likelihood, we can maximize this lower bound instead. And we can get a picture like this. So this is our marginal log likelihood. Let's imagine that it looks like this. And here we assume that it has just one parameter, theta. So the parameters are one-dimensional, which in practice is usually not the case, but so you can have millions of parameters, but it's much easier for illustration purposes. So it's much easier to plot some graphs in one dimension. And the marginal likelihood has the optimal parameter theta star, which we would like to obtain, but as we have already discussed, it's NP hard, so we cannot hope to obtain this theta star in reasonable time, so we'll be happy to find at least a local maximum of this function. Now we can lower bound this function. So we can find a function L, which is less than or equal to our marginal log likelihood at any given point. And we will build it in such a way that it's easy to maximize. So we can find its maximum theta star and use as a maximum as kind of proxy for the maximum of the original log likelihood of the blue curve. Well, it's kind of reasonable, but it turns out that actually we don't have any guarantees. The theta hat, the optimal of the lower bound, can be arbitrarily bad according to the blue curve. Here, for example, the theta hat almost almost appears in the local minimum of the log likelihood, and it's really bad, right? Like we wanted to maximize the blue curve, and we found something which we would like to use as its approximate maximum, and it's a local minimum. So we have to do something better. We have to do something else. Well, let's revise this idea of lower bounding. Instead of one lower bound, let's try to build a family of lower bounds, which all will, and when we will be able to choose among these lower bounds the one that suits us best at this current iteration or moment or whatever. So how to do it? Well, let's introduce some weights, some lever which will be able to change our lower bound. So let's introduce any distribution q on the latent variable t we want, and let's multiply and divide our function by this q. It doesn't change anything, right? Because we just multiply this thing by 1. But now we can treat this q as weights in the Jensen's inequality. So we can treat this q as alphas, and we can treat the joint distribution p of x and t divided by q as the points, as v. And now we can apply Jensen's inequality for the logarithm to this function to build a lower bound, which will look like this. And notice that it now depends on q, right? So we kind of succeed. We built a lower bound which depends both on the theta and on q, which we can now change to obtain different lower bounds and to choose the lower bound we would like to use on this current iteration or whatever we have. So now the picture looks like this. We have again our marginal log likelihood of the blue curve, and we also have a family of lower bounds like the orange, the red and the green one, and we can choose among them to find the best one. For example, we can choose the red one and maximize it with respect to theta, and its theta hat will be reasonably good approximation to the maximum of the blue curve. It will be somewhere in a good position. So how can we use this family of lower bounds on practice? Well, let's use this kind of iterative approach. So let's start with any point theta k. So it's the point from the previous iteration or maybe from initialization, and let's try to improve it in one iteration. So we have a family of lower bounds. Let's among this family find the lower bound which maximizes, which is maximal at this current point theta k. Which means let's find q such that the value of the lower bound L at the point theta k and q is maximal. And ideally, if we are able to maximize this thing to the optimum, we'll get something like this. Because this red curve, this red lower bound cannot be higher than the blue curve. So the best possible thing we can hope for is that they touch, that the lower bound becomes accurate at the current point theta k. And now we can go to the maximum of this lower bound, so to the point theta k plus 1, which is maximum of the red curve. And we hope that the lower bound is easier to maximize, so we can easily do these steps in iterations. And also, you can interpret the same thing we have just discussed in kind of block coordinate descent manner. So on the first substep, we're fixing theta k, and we're maximizing our lower bound with respect to q, with respect to distribution. On the next substep, we fix this best q, and we maximize our lower bound with respect to theta. So we fix one, we optimize with respect to the rest. And it makes sense, right? Because we have lower bound that depends on theta and q. So let's find its maximum with respect to both sets of parameters. And how to do it? Why not to use block coordinate descent? Why not to do in iterations like fix one, optimize the rest? And also note that this thing, this L, this lower bound, is sometimes called variational lower bound, because you can vary it. It depends on some parameter q, which we didn't have in the original model. You can do another step of this iteration, so now we're at the point of theta k plus 1, and we can also find the best lower bound at this particular point, and hopefully we'll find a lower bound which touches the blue curve at this point, and we can go to the maximum of this red curve, so to obtain the next point theta k plus 2. So to summarize, expectation maximization suggests you, so first of all we build a lower bound on the log likelihood, which depends both on the theta, which we want to maximize, the blue curve, the log likelihood, and the parameter q, which is something we just introduced. and it's also sometimes called the variational parameters. And it suggests you to optimize this lower bound in iterations by repeating the 2 steps until convergence. On the E step, fix theta and maximize with respect to Q, maximize the lower bound with respect to Q. And on the M step, fix Q and maximize the lower bound with respect to theta. So this is the general idea of the expectation maximization. In the next videos, we will discuss how to obtain these E and M steps efficiently.